Hello guys, so in this video we will discuss first partial decoding and then we will solve an example based on memory interfacing with 8085 microprocessor. Okay, so what is partial decoding? So first point is it is used in case of small systems. Okay, and it uses individual higher order address lines to select the memory chips. Okay, and on the other hand, in full decoding, okay, what was that? In full decoding some specified logic levels of higher order address lines are used, okay, to select the memory chips, while in this partial decoding it uses individual address lines. Okay, so for example we can say higher order address lines is from A8 to A15. Okay, so we can use any of the address lines between this A8 to A15, okay, while using partial decoding. So one conclusion can be made from this, and it is written as, one can say that hardware, okay, of the decoding logic can be reduced. Okay, it's very much obvious. Okay, but now the question is, why then it is not used, okay, as compared to that partial, linear decoding, okay, that is full decoding, absolute decoding. Okay, so the reason is that it has some drawbacks. Okay, and one of the drawback is of shadow address. Okay, so that's why it is not used, okay, most widely. Now we will discuss one pretty much good example based on memory interfacing. Okay, so now the example is interface 4 KB of EEPROM with starting address. This SA stands for starting address. Okay, 000H and 2 KB of RAM with starting address. Okay, this is starting address followed by EEPROM. Okay, the question is clear. Now how to proceed step by step. Okay, so first we will decide the number of chips we required, okay, for this purpose. So the step number 1 is total EEPROM required. Okay, how much it is required? 4 KB of EEPROM, okay, over here. So, and we have chip size available in market in form of IC, I think 2732. Okay, this is the IC. Okay, and it is of 4 KB. So we will require one chip. Okay, so chip required, we can say number of chip required equals to chips, we can say 1. Okay, now let's have the starting address of this chip 1. Let's say this is chip 1. Okay, so let's have the starting address for the same. So starting address is given 0000H for EEPROM. Okay, and now chip size is what? 4 KB. Okay, so 4 KB can be written as something like this: 0FFFH. Now the question is how it is written like this. Okay, so first let me tell you one thing. 4 KB is 1000H. In fact, actually, how it comes 1000H? 4K, okay, 4 means 2 square and K means 2 raised to 10. 1 KB is, okay, so total is 2 raised to 12. Okay, so in hex we can write it consists of 4 0 0 0 0. Then it also consists of 4 0 0 0 0. Similarly this 0 0 0 0. Okay, and this 1, so 1 0 0 0. Okay, let me write it again. So 0 0 0 1 0 0 0 0 0 0 0 0 and 0 0 0 0. Okay, so we can say that 0 2 raised to 0. Okay, 1 2 3 4 5 6 7 8 9 10 11, and this one is 12. So 2 raised to 12, that is 4 kb, can be written like this, but we write like this. Why so? Okay, simple. We have started from 0000h. Okay, so it is very much obvious that we have to subtract 1 from this, and so the result we will get is 0FFF. Simple. So these are hexadecimal only. Okay, so it is very much simple. Now let's start step number 2. Okay, so here we have ending address, this one, it is clear. Now let's proceed to step number 2. Okay, now here RAM required is what? 2 kb from the question. Okay, this is given 2 kb. Okay, now we have IC 6216 available. Okay, in the market of 2 kb size. Okay, so we will require only one chip, so number of chips required for the RAM is 1 only. Okay, so let's say this is chip 1 of RAM. Okay, this was of EEPROM. So its starting address is what? The question is saying RAM with starting address followed by EEPROM. Now EEPROM has ending address this. So the starting address of RAM will be what? This address plus 1. Okay, so we can write ending address of EEPROM plus 1. Easy. So we can write 0FFFH plus 1. So it will be obviously 1000H. This is the starting address. Now let's calculate the ending address. Okay. Now what is ending address for the same? Ending address is what? Chip size plus 1000H, that is the starting address. So chip size is what? 2 kb. Now how to write 2 kb in hex? Okay, 2 kb means 2 into 2 raised to 10. Agree? Total is 2 raised to 11. Okay, so simply we can write as before. Okay, 2 raised to 11 means 0 0 0 0 0 0 0 0. 2 raised to 0 1 2 3 4 5 6 7 8 9 10 11. Okay, and let's say 0, this is 0 0 0 0. So we can write what? 0 8 0 0. Okay, this is what? The chip size, or we can say we can write 2 kb as like this, but actually this is wrong. We cannot write like this. Now why so? Because we have started from 0 0 0 0 initial, so we must subtract 1 from this, and this will be the exact answer. So let's subtract 1 from this, so we will get 07FFH. Okay, all this will be 1111, so F 1111, so F 111, and lastly the 0. This will be 7 this will be F, this will be F, and here is 0 0 0 0 only, so this will be 0. Okay, so what we can write, 0 7 F F H plus 1 0 0 0 H. This is simple addition, so we can write 0 1 7 F F H, simple. So we got starting address and ending address. But now we calculated the starting address and ending address with all this stuff, that okay, uh, adding one and then subtracting blah blah blah. Okay, so I have some more quick method. Okay, this is the actual method, but I will give you the shortcut. Okay, so for that we will jump directly to step number 3, and this will be called as memory map. Okay, directly you will get the address, starting address and ending address. Just in step 1 and 2 you have to decide the number of chips. Okay, so how many chips are required, that only we have to decide. Okay, we will discuss memory map. Okay, and from that easily we can find the starting address and ending address without proceeding like before. Okay, so let's have it. So let me draw a table, or simply let me write first. Okay, this is EEPROM. Okay, EEPROM's chip 1. Okay, having starting address of 0000H. Okay, and ending address of what? The question is saying starting address is of 0000H. Okay, now EEPROM size is of what? 4 KB. Okay, so 4 KB simply can be written like this. Okay, so we will write 0FFFH. Okay, now we have 16 address lines, so let's write all those 16 address lines. These are 16 address lines from A0 to A15. Okay, now 0000 means 0000. This is in a hex, I am writing in binary. So this 4, then this 4, then this 4, and then last 4. Okay, now we have to write 0 FFF. This 0 means this 4 times 0. Okay, then F means 1 1 1 1, then again F means 1 1 1 1, and again F means 1 1 1 1. Okay, now this can be directly found out from the question only. Okay, just simply starting address is given, we will add the chip size and we will get this. Okay, okay, as proceeded before in this step number 1. But now let's move further to RAM. Okay, it's chip 1. Okay, so its starting address is what, followed by RAM. Okay, so simply just add 1 in it. Okay, so it will be what, simple, done. And ending address is what, as calculated, 17FF, so 17FFH. Okay, so this 1 can be written as 0001, then all are 0, so 0000, then again 40000, then again 40000. Okay, and then this 17FF can be written as 1 can be written as 0001, and 7 can be written as 0 triple one, then F can be written as 1111, again F can be written as 1111. Okay, now as discussed earlier, we have two decoding logics. Okay, first one is full decoding and other is partial decoding. Here we will use full decoding logic. Okay, we'll use what? Full decoding logic. Now what to do in this logic first? Okay, so what you have to do, find the smallest chip size. So here EEPROM is of 4 KB and RAM is of 2 KB. So smallest is of this. So 2 KB can be written as 2 into 2 raised to 10, that is 2 raised to 11. So what we have to do, just neglect, okay, what we have to do, just neglect lower order 11 address lines. Okay, that is 11 means what? From A0 to A10, total 11. Okay, and use remaining address lines. Okay, that is A11 to A15 for decoding logic. Simple. So we will do like this. So what we will do, we are remaining with this 5, okay, higher order address lines. So we will use what? 5 to 32 decoder. Okay, now how we will use 5 to 32 decoder? Okay, let me explain. So let me explain on the next page. Okay, so what we have to do, first, after deciding this logic, then we have to come over here again. Okay, what we have done, we have neglected first 11, okay, lower order address lines, okay, that we have neglected. We are remaining with this, so let me highlight it. Okay, we are remaining with this from here. Okay, simple. So what is this? This value is 0, so let me write y0 bar. These are the outputs of the decoder that we will use. Okay, I will show it later on. And this is equivalent to 1, so this is y1 bar. Similarly, the same procedure, both these are same only, so we will write only one, that is, this is equivalent to 2, so we will write y2 bar. Okay, now we will use what? Decoder. 5 to 32 decoder I said. So it has 5 inputs and 32 outputs, 1 2 3 4 5, and 32 outputs, y0 y1 y2 up till y31. So this is y0, this is y1 y2 up till y31. Now we have y0 bar dot y1 bar. All these outputs are complemented. We will use a decoder IC. All these outputs are complemented. Okay, we will use the decoder IC, okay, which gives the complemented output. Okay, so these are the inputs, A11 to A15. Okay, this is y0 y1. Now in EEPROM we are getting y0 bar and y1 bar. Okay, both are ended, so we will end them, and this will go where? This will go in the chip select of EEPROM, that is enable pin of EEPROM. And in RAM we have Y2 bar, so this Y2 will go to chip select or enable pin of RAM, and this to EEPROM. Okay, we will see. Okay, so this is the final step, implementation step. Okay, let me draw. This is 8085 processor. Okay, this is A8 to A15 higher order address lines. This is AD0 to AD7 multiplexed. So what we will do, simply we will use a 74LS 373 latch, okay, to demultiplex. Okay, we are knowing that this lower order address and data bus both are in time multiplexed form, so we will give it to the latch. Okay, and we know that ALE pin, this is 8085 processor, ALE pin, okay, this is STB enable pin also you can write. So it is given as an output. Okay, so when ALE is 1, then it is address, that is from A0 to A7, and these are A8 to A15. So combining both this over here, okay, so we will get what? Complete A0 to A15 address lines. Okay, and from here what we will get? We will get data D0 to D7. Okay, so by using this latch IC, this is latch IC, okay, we can separate address and data bus. Okay, that is lower order address and data bus. Okay, now we have this control pins, read, write and IOM. Okay, these three pins are given as input to 3:8 decoder. Okay, and this IC is 74LS138. Okay, now 3:8, so it has 8 inputs, but we will not use all the 8. We will use only the outputs which are required. Okay, remaining are as it is. Okay, so depending on some combination, I hope all of you are familiar with digital electronics. So this will give memory read, memory write, IO read, IO write, okay, and other combinations. So all this are provided to this. This is RAM, or let's take it ROM, EEPROM over here. Okay, and this one is RAM. Okay, so this is directly provided. Okay, so over here D0 to D7 comes. Okay, this is also directly provided. Okay, so over here A0 to A10 only will come. Okay, because other address lines are used for decoding logic. Okay, that we will see. This is the chip select pin. Okay, this is output enable pin. Okay, now we know that ROM, okay, is used only for reading the data. Okay, so memory read will be given to this chip. Okay, now this is RAM over here, this is enable pin. Okay, and this is we can say write enable, output enable, and this is write enable. So RAM is used for both the purpose, either to read or to write. Over here also we have chip select pin. Okay, so memory read pin, okay, will go in this, and memory write will go in this pin. Okay, now comes the part of decoder, that is decoding logic, full decoding logic, 5 to 32 decoder. Okay, so we have 5 inputs from A11, A12, A13, A14 up till A15, and we have different output combinations from Y0 to Y31. Okay, now as discussed earlier, this will be ended and will be given to the chip select pin of EPROM. Agree? So it will be given over here, and this alone will be given to chip select of RAM. Okay, so this is the complete process of interfacing the memory required, okay, to the 8085 microprocessor. If you have any doubt, this lecture is quite a bit bigger, so if you find any difficulty, you can ask me in comment section. Okay, and I have also solved the same problem, okay, in a very systematic and schematic way. So you can see this is step number 1, okay, which I already showed you. Okay, so you can just go through it. Okay, done. And then we have this full decoding logic. Okay, and then at last the whole interfacing in a proper way. Okay, so you can refer this. Thank you so much for watching.